Welcome to the first video of our rational functions unit. In this unit, we're going to start out with specifically just some definitions, and then going straight into all of the steps that it takes to find the characteristics of a rational function and how to graph it. So for this first part here, we're going to go through some definitions. The first one is rational functions. So that is the unit that we are going to be covering is rational functions. And it is a function that can be written in the form f of x is equal to n of x divided by d of x, where n of x and d of x are polynomials. So if you recall from the polynomial unit, a polynomial is something like x squared plus 2x, or it could even be x plus 1. Anything with x as a base is considered our polynomial. We kind of went through all the characteristics. So you're dividing two different polynomials. That's a rational function. And a vertical asymptote is a line x equal to a of the graph of f if the y values, so f of x, which is the y values, are approaching infinity, or if the y values are approaching negative infinity, either from the right or from the left. And this is an example of a non-removable discontinuity. And a whole, on the other hand, would be an example of a removable discontinuity, and we're going to explain in a little bit what that means. A horizontal asymptote is the line y equal to b. So notice vertical asymptote is x, horizontal asymptote is y, and in this case the y value at the x value of b, so f of b, is approaching b as the x values are approaching infinity or negative infinity. And again, we will also see an example of that and come back to the definition. And lastly, oblique asymptote. So an oblique asymptote is if the degree of the numerator of a rational function is exactly one more than the degree of the denominator. So for example, something such as x squared plus 2x plus 1, that's a second degree polynomial. And then at the bottom we have x plus 1. The numerator has exactly one more degree because it's a first degree at the bottom, so that would mean we have an oblique asymptote in this case. An example of a horizontal asymptote, an oblique asymptote, is sometimes called a slanted asymptote. It would look something like that, which we'll see in a little bit. A horizontal asymptote would look something like that. And so you see that as the x values move in either direction, right, as we move that way and as we move that way, they are still maintaining the same y value, which is whatever that height is of the line. A hole is just like what it sounds. It's a hole in the graph. That's a removable discontinuity because we can find the x and y coordinates of where that hole takes place, and we can fill in that hole once we know where x and y are. Our vertical asymptote is something that looks like that. And so the y values, if I switch colors here, right, the y values are approaching positive infinity or negative infinity at the same x value as x remains x equal to a. So those are our different asymptotes, our different discontinuities, because those are creating discontinuities, and they create a rational function, one example being something like this. And so this is a discontinuous function because in order to graph that, I had to pick up my pencil to draw the different pieces. And so that's because it has 1, 2 asymptotes there. So that's one example of a rational function. We're going to see dozens and dozens more as we go through this unit. So we are going to be going through these steps, but in this video we're only going to go through steps 1 through 4. There will be another video going through steps 5 through 7 coming up later. So the first step is, if we're going to graph a rational function, we want to be able to find the wholes of the function. So in order to find the wholes, we've got a couple of steps that we need to follow. And so the first step we want to take is we want to factor completely our rational function. So in this example, and I'm going to zoom in over here, so that means this is going to get a little smaller. There we go. 2x squared minus 8, I can factor out a 2 from that. So that leaves me with x squared minus 4 at the top times 2. And in the denominator, x squared minus x minus 6, that will factor to x minus 3 times x plus 2. Now this is not factored completely. It is at the bottom, but at the top, x squared minus 4 is the difference of 2 squares. So I'm going to break this down even further. That'll become x plus 2 times x minus 2 when we break it down, and then x minus 3 times x plus 2 at the bottom. So that takes care of the first step, is to factor, and step 2 is to see what cancels out. There's going to be some factors, hopefully, that cancel. If you look at the top, it's x plus 2, and at the bottom it's x plus 2. So those two cancel each other out, and that is telling us where our whole is going to take place. So what we do is we take that factor that we just canceled out, and we will set that equal to 0. Sorry, I don't know why I wrote y. X plus 2 equal to 0. And then we solve for x. We get x equal to negative 2. That is telling us the x coordinate of the whole. Because the whole is taking place, the place of a point, we need to have an x and y coordinate in order to have a whole. So we have figured out the x coordinate, we need to find the y coordinate, and so what we will do is we will go back to our equation, but now it's a simplified equation. It's 2 times x minus 2 over x minus 3, because that x plus 2 got canceled. And what we will do is take this x value that we've already found, we know that's where the whole takes place, and plug it in to the x's here and wherever else you may have it if you're working on a different problem, and solve for y. So what that would do is we would get y is equal to 2 times negative 2 minus 2 divided by negative 2 minus 3, and when I simplify this, I get 2 times negative 4 over negative 5 equals negative 8 over negative 5, which is positive 8/5. And that is the y coordinate. So now that I have found my x and y values, I know that the whole will take place at negative 2, 8/5. And that is my solution for that whole. We'll do another example here. X squared plus x minus 12 divided by x plus 3. So like in the first problem, the first step is to factor. So I am going to break down x squared plus x minus 12 to x minus 3 times x plus 4, and that's all divided by x plus 3, because I can't really factor that any further. So what I will do from here is, now that everything is factored, because it's all in its simplest form, I need to see what cancels. And I have an x minus 3 at top and x plus 3 at the bottom, but those are not the same, so it's not going to cancel. So when nothing cancels, that means our function has no whole. Okay, for this next problem, y is equal to x minus 5 divided by x squared minus 2x minus 15. Again, we will factor. So that will become x minus 5 at the top since it's already in its simplest form. But at the bottom, it becomes x minus 5 times x plus 3. X minus 5 is going to cancel here. So that means my x coordinate, if I set that to 0, will be at 5. So I found my x. Now I'm going to come back here. If the x minus 5 gets canceled, I'm still left with the 1 up top and just an x plus 3 at the bottom. And from here I will go ahead and plug in that 5, which gives me 1/8. So my whole will be at 5, 1/8. Next problem is partially factored. We have x minus 1, which is already factored, but x squared plus 4x plus 4 can be broken down a little further. So let's go ahead and do that. This will become x plus 2 times x plus 2. That is a perfect square right there. And the bottom will factor to x plus 3 times x minus 1. So I can see that the x minus 1s, those cancel. So I'm going to set that equal to 0. Oops, that should be a minus there. And solve for x. X is equal to 1. And so I can take that, plug it in to my oh, I didn't simplify yet. Let's go ahead and simplify. X plus 2 squared, technically up top, just to simplify it a little. X plus 3 at the bottom. And when I plug in the the x coordinate, that's going to become 1 plus 2 squared over 1 plus 3, which will become 9/4. That's my y value. My x is 1, so that means my whole is at 1,9/4. Okay, moving on to steps 2 through 4, which is to find the vertical asymptotes, the zeros, and the y-intercept. You'll notice that this is the same example that we did for the whole. So we've already found the whole, we've already canceled out the whole. So this step is kind of following from that. Remember, we canceled those out and we found the whole at x equal to -2. And we were left with this simplified equation. So now that it's simplified, this is going to be the equation that we're going to use to find vertical asymptote 0 and y-intercept. So we'll go step by step. To find the vertical asymptote, which I just simplify as VA, you want to take that simplified denominator and set it equal to 0. So x minus 3 equal to 0 gives me x equal to 3. That is where my vertical asymptote will be. Easy as that. If we had more than one term, then you would set each one, but we'll see an example of that soon. The zeros, if you look in step 2 here, all you have to do is set the numerator equal to 0 to find any of your zeros. So my numerator here is 2 times x minus 2. So I will set that equal to 0. And then solve for x, so that gives me x is equal to 2. That's where the 0 will be. And remember, a 0 is the same thing as a x-intercept. And lastly, we have our y-intercept. So the y-intercept is when the graph intercepts the y-axis. And to find that, we will need to take this simplified equation here and plug 0 in for x. all of the x's. And then we simplify. 0 minus 2 is negative 2 times 2 is negative 4. Divided by negative 3 gives me 4/3. So y is equal to 4/3 is my solution for the y-intercept. Let's move on to example B. So again, in example B is the same one that we did earlier. This is the one where we found no zeros. So we did not cancel anything out. That means this is our simplified term because there was nothing to simplify. So this is what we're going to use to find our next characteristics. So starting with the vertical asymptote, to find the vertical asymptote, you set the denominator to 0. In this case, our denominator is x plus 3. Set that to 0, we get x is equal to negative 3. There's our vertical asymptote. Next comes the zeros. Take our numerator and set it equal to 0. So we have x plus 4 times x minus 3 set to 0. And when we have things that are multiplied and equal to 0, we can easily just set each to 0. I don't know why I put the parentheses there, but x is going to equal negative 4, and x is going to equal 3. So that means we have two zeros in this case, or two places where the graph is going to intercept the x-axis. And then lastly, our y-intercept. We plug in 0 for all of those x's that were left, or in this case we're just there because we didn't cancel anything. So this same equation, just plugged in 0, and that's going to give me 4 times negative 3 over positive 3 is negative 12 over 3 equal to negative 4. So that is my y-intercept for this problem. Now for this next problem, we had already found the whole. That was 5 and 1/8. And this we had already simplified to 1 over x plus 3. So the vertical asymptote is when you take the denominator and set it equal to 0, and that is going to give us x is equal to negative 3. The zeros is when you take the numerator and set it equal to 0, but in this case, we can't do that because we don't have any x up at the top. So this means we have no zeros in this case. And finally, the y-intercept, we are going to plug in 0 for that 1x that we have there, and we get 1/3 as our one and only y-intercept. One thing I also forgot to mention is that intercepts and zeros are technically points. So another way we can write this, if you don't leave it as y equal to 1/3, we want to write it as a point. So it would be 0, 1/3, okay, because then that's actually an intercepting point rather than a line. So I just want to make that distinction. I did forget to include that over here for these values, but you can go ahead. The zeros, this would be negative 4, 0, and 3, 0. So we do often just write zeros as x equal to negative 4, or y-intercepts as y equal to negative 4, whatever it may be, but remember they are points, so they have that 0 component to it. And this last problem, again, it's the problem that we did before. Those x minus 1's got canceled, leaving us with x plus 2 times x plus 2 all over x plus 3. So we had our whole that we had found was 1, 9/4, and now we're going to go ahead and find our vertical asymptote, which would mean we take that denominator, set it equal to 0, that gives us x is equal to negative 3. And then for our zeros, because we have x plus 2 repeated twice, x plus 2 times x plus 2 equal to 0, technically we have x equal to negative 2, but it has a multiplicity of 2 because it's repeated twice as a 0. So we want to make sure and make that distinction, and we'll just say x is equal to negative 2 with a multiplicity of 2. So that means it's a 0 at negative 2 twice. And lastly, the y-intercept, we plug in 0 for those x values, so 0 plus 2, 0 plus 2 over 0 plus 3. And that becomes 2 times 2 is 4, over 3 is 4/3. And that concludes our video here. Keep a lookout for steps 5 through 7 in the next video. Goodbye.